What I wanted to have a look at today is deriving Newton's method. Newton's method is actually new to the VCE methods course. It's part of the sort of pseudocode section and looking to introduce algorithmics. It's also something that there's not heaps of resources about out there. So hopefully this video you'll find instructive. I think it can be hard sometimes to follow a textbook definition, so this should hopefully be quite a visual demonstration. So, and you only need really year 9 maths to really wrap our head around this. And then maybe later on we can do an example. But this video will just be a definition. So first thing I'm going to do is I'm going to start with the function f of x. Got to keep that in mind. This function has some x-intercept. And remember, we're doing this generally. So this x-intercept could be anywhere. There are a few caveats about Newton's method that we need to be aware of later on. But for now, we've got some function. It's got some x-intercept. What we're going to do is we're going to draw a tangent to that function at some point, and this is our red line. So somewhere along here, it tangents, that red line tangents to it, and we're going to call that point x sub n, okay? And this is important because what we're going to get soon is a recurrence relation. I'm going to call that point x sub n, and we're going to draw a little triangle around our points. So if this point here is an x value of x sub n, then the x value at this coordinate here, at the intercept of this tangent, must be x sub n. And given that it's in a tangent, it must have the y coordinate of f of x sub n. Okay, and then the next important thing to note is that this point down here is what we're going to call x n plus 1. So this is our next x value that we got, and that's the intercept of the tangent of the graph on the x-axis. So it's our new x-intercept. You'll notice, and this is what the whole point of Newton's method is we're going to get closer and closer to this true x-intercept. So you can see that this xn plus 1 is already a fair bit closer to the true value of this x-intercept already. And as you'll see as we go along, that's just going to get better and better. So we're going to basically follow the same process, and it's an iterative process. So what that means is we keep doing that. So at this x sub n plus 1, we're going to draw a perpendicular line there. And then again, we're going to draw a tangent at that point. And what we'll get is we get another triangle. So you can see we had the red triangle, now we've got this smaller blue triangle. And if we zoom in a little bit, you can see, and then we get this new x-intercept here for this blue tangent line, which is even closer to the true x-intercept. And stretching the powers of my computer here, if I zoom in, you can even keep going. If I zoom in even more, we can get a purple line. We draw up another perpendicular, we draw another tangent, and now these points are so close together, that's almost indistinguishable. So you can start to see how by doing successive tangents to our line of f of x, we can get increasingly better approximations of the x-intercept of the green function. Now you might be wondering, why is this useful? We can always use calculus to find x-intercepts or some other method. But this is kind of, and the reason it comes in coding is because this is how a calculator would have to do it. It has to use some process, some iterative process, in order to output the values that appear on your calculator. So after 3 or 4 iterations of Newton's method, this is going to be very accurate. So if we keep going, we can sort of start to say the following. If we look at the gradient, so let's have a think about this red triangle. This red triangle, we know that the gradient for anything is rise over run. Well, if we just look at this red triangle, the rise is going to be f of xn, f of x sub n. That's how high up it is. And the run, well, the run is just the difference between these 2 points. So it's x sub n minus x sub n plus 1, which is what we've got written over here. We're saying that the rise over run is f of x sub n divided by x sub n minus x sub n plus 1. Now, what we're doing here is we want successively better approximations of the x-intercept. So what we're really interested in is this x sub n plus 1, because that's always the next term. So it's always getting better. So if you've ever done any recursion relations, it's tightly linked to that. Now, this next line here says that and this is where it requires a little bit of calculus. It's saying that at this point here, the derivative of the function f dash, the derivative of the function f of x is f dash of x. So the value of the gradient at this point is also equal to f dash of x sub n. So this is where we just introduce a bit of calculus. We're saying, the gradient, just sort of by looking at our triangle, is this thing on the right-hand side, but we also know that that's going to be equal to the derivative of the function at x sub n. And then we're almost there. What we want to do now is we want to rearrange for x sub n plus 1, because that's always the next term, and that's the thing we want. We want to get successively better. So just do a slight rearrangement here. There's nothing crazy going on here. Just divide f dash of x sub n underneath f of x sub n. And then we just rearrange, and basically this formula falls out as our Newton's method, and this is the form for Newton's method. X sub n plus 1 is equal to x sub n minus f of x sub n divided by f dash of x sub n. So that was all quite abstract, but hopefully you can sort of see the process that's going on here. You're just getting successively better tangents, and the more and more you do that, the better the approximation of the x-intercept of the actual function becomes. So a bit of a mouthful. Hopefully the visualization helped a little bit there. We might come back later and do an actual example of Newton's method in action. But otherwise, hope that was helpful.